Hello, my name is Bernardo Sandoval. I am a computer science undergraduate in Federal University of Santa Catarina. The work I'm presenting is Exploring Gate Mapping and Transistor Sizing to Improve Radiation Robustness, a C17 benchmark case study. This work schedule is Introduction and Motivation, Methodology, Results, Split and Voltage Supply Evaluation, and Gate Mapping Evaluation, and finally, Conclusion. With the development of new technologies, transistor sizing continuously decreases. With this reduction, new transistors become more susceptible to faults, one of these being the radiation fault. When a charged particle comes into contact with a specific part of a combination circuit, it may cause a single event transient, or SET, which alters circuit behavior. That is, it can change the logic signal as impacted node, and, consequently, in all nodes that depend on its value. These challenges remain valid in FinFET technology, which is the main focus of this work. These transistors have an enhanced robustness due to their 3D structure. However, when considering aerospatial and low-power applications, radiation evaluation still is a key constraint. There are different ways to deal with radiation. This work deals specifically with logical and electrical masking. Logical masking deals with how alternate topologies of the same circuit affect its robustness. This is explored by investigating how gate mapping affects the robustness. Electrical masking deals with how the physical properties of the circuit affect its robustness, which is explored in this work through transistor sizing. This experiment uses the C17 benchmark in 5 different topologies to investigate its effects. Shown in the image is the standard topology of C17, and here the 5 alternative versions. The SET faults are modeled as current pulses, uninjected one at a time in each node of the circuit with each input vector. These simulations are administered through a Python script that runs the simulations in HSpice. The script considers both 101 and 010 pulses in every node. The image presented shows in green what the 010 pulses look like, and in purple a 101. The script then determines which node is the most sensitive, that is, which node requires the lowest current to change the logical signal of any output. The value of this current of the most sensitive node is then converted to the linear energy transfer threshold, or LED threshold for short. This value is unique for each circuit and represents how sensible the circuit as a whole is. The lower this value, the more sensitive the circuit is. The complete evaluation is made with the circuits operating in voltage supply ranging from 0.7 volts to 0.4. After performing all simulations, it is possible to compare the circuits and determine which one is the more robust. 2 questions are considered to help determine the better topology. The first is how the circuit supply voltage affects the LED threshold, and the second is how the gate mapping impacts the robustness. This table shows LED threshold for each version of C17 operating at 0.7 volts. These absolute values are presented as a reference, since the physical parameters may vary for industrial devices. The focus is to show the comparison of robustness between them and how they vary given supply voltage and sizing variation. All circuits have an output as the most sensitive node, version 0 having both at the same sensitivity. Also, the circuits divided into very distinct groups, version 0 and version 2 being clearly more robust than the others. This tendency continues when considering different supply voltages for the circuits. The circuits keep split into 2 groups, where version 0 and 2 remain more robust than the rest. The pulse type and the most sensitive node do not change with the supply voltage, and for every 0.05 volt supply drop in voltage, the LED threshold decreases, on average, by 12.31%, that is, when compared to 0.7 volts. The operation near threshold below 0.5 volts provokes a reduction of over 75% on set cell robustness. These values can even be found at Earth's surface, not only in space. When considering only the value of the last threshold, version 0 and 2 seem to have the same robustness, but the discussion can be deepened. The last threshold is associated with a node, a pulse, and a group of input vectors. The important part is that not all input vectors allow the last threshold. Some input vectors might allow a let of value different from the last threshold, or even no let at all. Therefore, it is important to know how many input vectors allow the let threshold of each circuit, and the tables shows just that. Version 2 has its let threshold occurring less frequently than version 0. Therefore, even though their let threshold have the same value, version 2 is frequently more robust than version 0, since its let threshold occurs less often. With this information, we can now conclude that version 2 is the more robust of the 5, and also, by the same reasoning, we can conclude that version 1 is the less robust of the 5, and version 3 and 4 present the same robustness. Still, regarding the C17 versions, we can go deeper by investigating the reason for the division of the circuits into two different groups. This reason is gate mapping. All circuits in the most sensitive group have an OR as the sensitive output, while the more robust have an AND. This explains why C17 version 0 has both its outputs as the most sensitive, since both are NAND gates. The conclusion that the output gates dictates the robustness motivates us to do an individual gate analysis, and, using the same methodology, now in the individual gates, we obtain the following results for the robustness of each gate. As we can see, the NOR gate has the same threshold value as the more sensitive versions of C17, while the NAND gate has the same for the more robust. Furthermore, we can ask which transistors have the most impact on the lot threshold of each gate. By measuring the lot threshold of the gate before and after we size each transistor, we can determine which one is more relevant. It was observed that the pull-down network matters the most in the NAND gate, and the pull-up in the NOR. That is, for both gates, the arrangement of transistors in series impacts the robustness the most. The table below shows the threshold of the NOR and NAND gates with different combinations of transistor size. 3 fins were adopted as the base size and 5 as the size one. The sizing of the parallel network never affects the lot threshold, except in the all category. In the case of the NOR gates, the gain with the sizing of both P1 and the P2 transistors and sizing all transistors is very similar, making it possible to have significant gains in robustness with minimal penalties in area. Now, considering this data, two mitigating approaches can be made: sizing individual transistors of multiple gates, or inserting an inverted buffer on all outputs, that is, two inverters in series, in a way that it doesn't affect the logical signal at the output. Both approaches were done with the circuits operating at 0.4 volts, since it's a range where circuits are more sensible. An important detail about sizing individual gates is that only the robustness of the node's internal and at the output of the gate increase, not in the circuit as a whole. Because of that, to increase the robustness of the whole circuit, every sensitive gate has to be sized, resulting in the following. Here, each gate size implies that only the transistors from the series network were sized. The effectiveness of this technique varies drastically based on the circuit. This happens because NOR gates gain much more robustness than NAND gates when compared only the series network. The robustness of versions 1, 3, and 4 increase much more since they have multiple NOR gates, which are more responsive to this approach. Since versions 0 and 2 don't have any, this approach isn't as effective. Despite that, once the NOR gates from the first 3 versions are sized, increasing their robustness becomes costly, since it would be necessary to size their NAND gates. Here we have the gate size for version 0, and here for the alternative versions. It's important to notice that in version 1, 3, and 4, only NOR gates were sized, with exception of a single OR gate in version 4. The other, more simple approach is the inverted buffer insertion. The following table shows the result for both circuit groups. In contrast with the individual gate sizing, this approach increases the robustness of every node in the circuit, not only the part affected. However, the robustness gain is not as good as the previous approach. Here we have only 10% as the best increase, while in the former we had 69% as the best. In conclusion, this work evaluated the robustness to radiation of 5 different topologies of the C17 benchmark using 7nm FinFET. It was concluded that although version 0 and 2 present the same LEP threshold, version 2 presents superior robustness due to lower input combinations related to its LEP threshold. This shows that small changes in the circuit, like replacing some gates and interconnections, can improve the circuit robustness with minimal penalties in area. The supply voltage evaluation shows that the radiation susceptibility is still a key concern for FinFET design, since radiation levels found in Earth's surface can cause sets faults to circuit operating with low voltage supply. The individual gate evaluation demonstrates that the sensibility of the output gates are the main reason for versions 1, 3, and 4 low robustness. This information can help designers decide among different topologies. Furthermore, this work explored transistor sizing and buffer insertion to increase radiation robustness at near threshold operation. The adoption of transistor sizing only in the most sensible gates minimizes the area overhead by increasing the number of fins, showing up to a 69% of improvement in robustness. Alternatively, the simpler approach gained 10%, which, although is not as good as 69%, still is a very cheap approach to mitigation. The results of this work will be expanded to other benchmarks and larger circuits to provide a set of tools and data to aid designers doing the technology mapping for more reliable circuits. Finally, we would like to thank the research support given by CAPES, CNPq, and NUVSC. Thank you.